All right, so today we're going to be talking about triangles and trigonometry. Um, some of this will be review of what you learned in your geometry class, others of this will be new content. So why don't we start with the review part. So one thing to note as we start doing more trig is there is a setting in your calculator that you should pay attention to um, as you're working. So just a quick note, be sure that the calculator is in degree mode. So real quick, as we're about to do work, or pretty much any time you start on a trig problem, double check that your calculator is in degree mode. Degrees and radians are basically two different units that can be used to measure angles. IB always sticks to degrees. If you're getting some really small decimals or negative answers where you are like trying to find a side length, that is usually because your calculator is in the wrong mode. But hey, if we're going to be talking about triangles, we're also going to be looking at a lot of triangle diagrams. And there are some conventions that are used for them that we should talk about. So if we have a triangle, and this one I'm intentionally not going to make a right triangle, just some kind of random triangle, then the thing to note is that capitalization matters. What I mean by this is that we want lowercase letters to represent side lengths and then uppercase letters represent angles. And this is a convention that you'll see me follow. It's also a convention that IB follows in the questions that they write. So in these problems, you'll see a lot of A's, B's, and C's thrown around, and the lowercase and uppercase capitalization does matter. So for example, we have three angles in a triangle. We'll call them capital A, capital B, capital C. Actually, let me draw that C a little bit bigger. Capitals. And then the side lengths are always the sides named after the angle opposite them. So if this is angle A, then side A is this one. So this is side lowercase a, side lowercase b, and side lowercase c. If you have a right triangle though, so this time if I draw a right triangle, that means that this is my right angle, so I can denote it with that little square. In this case, we always want to make sure that our hypotenuse, so the hypotenuse is the side that is opposite the right angle, is always side C. So we'll have angle A and angle B, which makes this side B and this side A. But the important thing here is in a right triangle, C is always the hypotenuse. And clarifying this is going to be really helpful when we get to using the Pythagorean theorem. All right. But the other kinds of diagrams that you'll see a lot, instead of just labeling the angles and sides, are labeling the sides as opposite, adjacent, and hypotenuse, right? So anytime you see trig, you should be thinking, oh, we're going to be looking at sine, cosine, and tangent, which means that you have to label opposite, adjacent, and hypotenuse. And I think a lot of the times one of the most common mistakes that I see comes in messing up those labels. So let's go over that just to minimize the number of mistakes that we can make. So our header is labeling opposite, adjacent and hypotenuse. All right. And the important thing to note here, because I know this is something everybody's always done, the common mistake is thinking that there's only one way to label it. So it's important to note that the opposite and adjacent labels are always relative to an angle. So what that means is if we're looking at a different angle, still within the same triangle, your opposite and adjacent labels might change. And let's see an example of this. So I'm going to draw more triangles. And these triangles we will make right triangles. And let's actually draw two of them. Actually, let me just duplicate this. Okay. So let's say we have our angle theta here. And that is the angle that we are interested, or the angle that we have a measurement for. In this case, the way I decide which side is my opposite side is usually I'll put my finger on my angle. So let's pretend this red dot is my finger. The opposite angle, the opposite side is always the side that I'm not touching. So I am touching this top side, I'm touching the bottom side. So that must mean that this side right here is the opposite side. So if you've had trouble identifying which side to be your opposite and which side to be your adjacent in the past, that is one helpful way to do it. Then the adjacent side becomes the side that has both the right angle and also your chosen angle theta. And the hypotenuse is the longest side. I know a lot of people tend to remember that, and also the side that is opposite the 90-degree angle. But let's say we have this exact same triangle, but instead of putting my theta here, so instead of working with this angle, what if instead we work with this upper angle? So what if instead we work with, actually let me use a different Greek symbol. Instead of theta, I'm going to use alpha, which looks like a little fish. So this is the exact same triangle, but now if I put my finger on angle alpha, the side that I am not touching is actually this side. So in this situation, my opposite side is the one on the bottom. The adjacent side is still the side with alpha and our right angle. And then you'll notice though that the hypotenuse doesn't change. So because the hypotenuse is always defined relative to the right angle, as long as your right angle isn't changing, neither is the hypotenuse. So be careful with that. Just because you have one triangle and you're doing all this math and you already made your labels, these labels are dependent on your angle. So if the angle changes, so do your opposite and adjacent. All right. So I'm going to draw out a few different triangles and we'll practice working with these labels. So there is one triangle. And then let's put a really skinny one here. And then one more. All right, one thing to note is that, and this is really important, opposite, adjacent, and hypotenuse as ideas are for right triangles only. So in the past, in your older geometry classes, you've done a lot of right triangle trig. So everything that I've said so far should be some kind of review. In this class, we're going to learn some tools that work for right triangles, and we're also going to learn some tools that work for non-right triangles. And so it's important to make this and keep this distinction in your head. So if we are going to label opposite, adjacent, and hypotenuse for all of these triangles that I have just drawn here, then they all need to be right angles. And so we should put in our right angles. All right. Okay. So for each of these, we're just going to label the sides with O, A, and H relative to our angle theta. And so in order to do that, I need to give you an angle theta. And that theta is really just marking the angle that you have a measurement for. So if you know that this angle is 32 degrees, usually we work with that particular angle if we don't know this one. So in this case, here's my angle theta. Here's my opposite side. So I can just label it with an O. My hypotenuse is opposite my right angle, and the adjacent has both the right angle and theta with it. So here's my opposite angle, or opposite side, that is opposite my angle theta, hypotenuse, and adjacent. This one tends to be a little bit trickier. Here's my hypotenuse, because here's my right angle, so I'm going straight across from that. If I put my thumb, or any kind of my finger, on my angle theta, the one side I'm not touching is this one, so here is my opposite side, and then the adjacent side is up top. Alternatively, you can start with the adjacent. Well, here's my angle theta, here is my right angle, so the side that connects them is the adjacent side. All right, so now we've set up all this opposite, adjacent, hypotenuse. I trust that we know how to label our sides. Why do we do this? Well, of course, we do it for our functions sine, cosine, and tangent. So sine, cosine, and tangent. Oops. So this is where our acronym SOHCAHTOA comes in. If you remember it, sine of our angle theta. And theta is always an angle, so the thing that you plug in into these parentheses is always going to be an angle measurement, not a side measurement. So sine is the same thing as, or sine of theta is equal to the opposite over hypotenuse. Cosine of theta is adjacent over hypotenuse. And lastly, tangent of theta is opposite over adjacent. So if you've ever wondered and not understood where that acronym SOHCAHTOA comes from, well, we have an S, O, and then H, so that's so. Ka comes from C, A, H, and then TOA is T for tangent, O, and A. So if that acronym helps you remember these ratios, go ahead and use it. I think we'll be using these ratios enough that you'll become pretty familiar with them. The other thing is, when we work with sine, cosine, and tangent, we also work with inverse sine, inverse cosine, and inverse tangent. So to find an angle, let's say you wanted to get theta by itself. So if you had this equation all set up, something like sine of 44 degrees is equal to 2 over 7 or something. Oh, wait. Wait, if you had a ratio, this makes more sense. If you had a ratio sign of theta is equal to 2 over 7 and you're solving for your angle theta, you're trying to get theta by itself, the thing you have to do is you have to undo the sign. You have to undo the sine function to get theta by itself. And the way we do that is with the opposite of sine, which is just the function that we call inverse sine. It looks like sine with a little -1 exponent, but it's not an exponent, it's just the name of the function. And similarly, if you want to undo cosine, then we would do the inverse of cosine. And try, if you are working in groups or recording a video about these angles, don't call them cosine to the -1. It's not an exponent. This is inverse sine, inverse cosine, and then also inverse tangent. All right, so let's see a few examples of how to use sine, cosine, and tangent, and also inverse sine, inverse cosine, and inverse tangent. So in this first problem, we've got our angle x. We have, our side x that we're looking for. We're given an angle, and we're also given another side. And so what you'll notice first is that all of these pictures are pictures of right triangles because sine, cosine, and tangent as ratios can only be used for right triangles. So go back and add that note. Sine, cosine, and tangent are also right triangle only. I know that this is a really familiar tool to a lot of you, and so later on in the unit, when people start to get confused, I see them trying to apply these three ratios to everything. And the thing you now need to think about is that triangle that I'm looking at a right triangle? Because if it is not, we can't use sine, cosine, and tangent. Again, because hypotenuse as a concept only exists with right angles. All right, so in number 1, the first thing we want to do is start with our labels. So here we have our angle theta, it's 39 degrees. If I put my finger on my angle theta, the side I'm not touching is this one, and so therefore x is on my opposite side, and 103 is my hypotenuse. So looking at our three triangle ratios, sine, cosine, and tangent, I want to know which ratio uses opposite and hypotenuse. Well, in this case, it's sine. So I want to set up a ratio using sine. So sine of theta is equal to opposite over hypotenuse. And if we plug in our given information, well, theta is 39 degrees. The opposite side is x, that's what we're trying to find out, and my hypotenuse is 103. Right, so from here, in order to get x by itself, what we're going to do is multiply both sides by 103. Right, that handy dandy trick of multiplying by the denominator of the fraction to get rid of it. And so on our next line, we get to bring x down. X is already all by itself. Then we just need to take that quantity and plug it into a calculator. And again, make sure that the calculator you are working with is in fact in degree mode, because if it is not, you will get a kind of funky answer. But 103 times the sine of 39 degrees is 64.8. And technically in my calculator it says 64.82000028. Now that we have learned the rounding rules for IB, you should be consistently applying them. So again, with your answers, you've got the choice of either writing out every single decimal that the calculator gives you, or rounding to 3 sig figs, which is what I have opted for in this situation. And also, I'm going to include my units, because those are the units we were given right there. All right, let's try another one. We have our angle, 61 degrees. This becomes our adjacent side, that 5.15 meters is the adjacent side, and x is the hypotenuse. So look for the ratio that uses adjacent and hypotenuse, and it looks like it's cosine. And so now we set up a ratio. Cosine of 61 degrees is equal to adjacent over hypotenuse. So this is 5.15 over the hypotenuse x. All right, well now x is in our denominator. So here, in this first question, we could just multiply everything by the denominator to get x by itself. In this case, what we're going to have to do is an extra step. So we'll start still by multiplying both sides by x. And what's going to happen at the next step is now I have an equation x times the cosine of 61 is equal to 5.15. And so to finish up getting x by itself, I can divide both sides by cosine of 61. Because remember, the cosine of 61 looks a little bit different than the numbers we're used to working with, but it is just a number. So if this is x times cosine of 61, to undo it, I can divide. And so now in my calculator that is in degree mode, we're doing 5.15 divided by the cosine of 61, which is 10.6 meters. All right. Then I'm going to skip over to number 4 to show you how to use an inverse sign, or inverse function. I don't know that it's sign yet. So like all these problems, we're going to start with our labels. My angle x is my theta. So I know I'm going to need an inverse trig function because I have an angle that is my unknown. But opposite that angle is the 40, and adjacent to that angle is the 50. So from here, the ratio that uses opposite and adjacent is tangent. So if I set up tangent of theta is equal to 40 over 50. And now to get tangent by itself, what we're actually doing is applying tangent to both sides of this equation. So just like you can multiply both sides of the equation by 103, you can also apply the inverse tangent function to the left and the right side. Though this side will look a little bit funky as I apply it. We're going to apply the inverse tangent function to both the left side and the right side of the function. And what happens when you do that is inverse tangent and tangent are going to cancel out, leaving us with theta by itself. And then on the right side, we just have inverse tangent of 40 over 50. And this is something you can just then type into the calculator. Inverse tangent of 40 over 50 tells us that theta is equal to 38.7 degrees. Don't forget your units. And that is theta to 3 significant figures. So here are the answers for questions 3, 5, and 6 above, but I will leave it to you to double check your own work. And now, so that was a review of right triangle specific trigonometry. And now what happens if you get a triangle that isn't a right triangle, because there are plenty of those out in the world. What are tools that we can use to understand those? And so one of them, so one of the two that we are going to learn is the law of sines. So now you can't just say like sine, because that could be referring to sine as the ratio opposite over hypotenuse. It could also be referring to the law of sines. So if you are finding yourself in a situation where you have to explain something, be sure to specify. So law of sines can be used for all triangles. It doesn't matter if it's a right triangle or not. And the formula is that lowercase a is equal to sine of capital A is equal to b all over sine of capital B is equal to c all over the sine of capital C. And so here I'm using the naming conventions that we talked about at the very beginning. Those lowercase letters all represent side lengths, and the uppercase letters all represent angles. So for sides, A, B, C, and angles, capital A, capital B, capital C. And I'm specifying this because I think one of the mistakes I usually see is students just like plugging numbers in the wrong spot. So sine, cosine, and tangent as functions always take in angles. So the number that goes in there has to be an angle. And so the numerators of each of these fractions is going to be the side lengths. The thing to note here is that you're only ever going to use two fractions at a time, not all three. So if you might set up a fraction that uses side and angles A and B, or you might be comparing side and angles B and C, but you never need to set up an equation for all three of these. And basically, to use this formula, so how do you know when you can use this formula? Oops. To use this formula, look for two side angle pairs. Because later on we're going to see kind of just a bunch of triangles jumbled together. Some of them will be right triangles, some of them won't, and it's going to be a puzzle to figure out which of these many tools that I have can actually be applied. So if you can find two side angle pairs, the law of sines is usually a good bet. But what does that actually look like? So let's see an example. Draw a triangle. And again, this is not a right triangle. Let's say we are looking for side x. We know that this other side is 24 centimeters. We know that this angle is 118 degrees, and we know that this other angle down here is 22 degrees. And so how do we find our missing angle, our missing side x? All right, what do I mean by two side angle pairs? Well, here I have my angle 22, and it matches with side x. That's awesome. And then I need another complete pair to compare it to, right? So I could use this angle, but I don't have any information about the side opposite it. And I could use this side, 24, but I don't know anything about this angle. So I need to find an extra piece of information in order to be able to use the law of sine on this triangle. That extra piece of information is triangle angle sum. So if you remember, triangle angle sum. And what it tells you is basically if you add up all the angles in a triangle, and this one, they should add up to 180 degrees. And so using that fact, I can find this side, and once I find that missing side, I will have one complete side angle pair right there. So just to show my work, I'm going to call this missing angle y. So I know that 118 plus 22 plus our missing angle y is supposed to equal 180 degrees, and so y must be 40 degrees. Cool. All right. In that case, here are my two side angle pairs. I've got my side x with my angle 22, and I also have my side 24 with its opposite angle 40. And I'm going to set up my law of sines using these two side angle pairs. So in the numerator of this formula is my side. So I'm going to start with the 24. So my fraction, my setup is 24 all divided by the sine of its corresponding angle, which is 40. And I'm going to set that equal to x, which is my missing side, all over sine of its corresponding angle, which is 22 degrees. And there is my formula. It's all set up, and it's going to help me solve for x, and I can solve for x by cross multiplying. So on one diagonal I have 24 sine 22, and on the other side I have x sine of 40. So to get x by itself, we can divide both sides by sine of 40. Don't want to introduce too many colors right here. I'll write it a little bit smaller. I'll divide both sides by sine of 40. And that gives me x all by itself on the right side. And on the left side, if you do 24 times sine of 22, all divided by the sine of 40, we get that x is equal to 13.986, etc. So if I'm rounding this to three significant figures, it's actually going to round up to 14.0 centimeters. So our missing side x here is 14 centimeters. Right. But this law of sines is really nice because it actually also, it does work for right triangles. So let's see one more example of how to use the law of sine using a right triangle. So let's draw a right triangle that is pointing down. We'll call this top side 17 meters, the hypotenuse 27 meters. We have this angle 51 degrees, and we have our missing angle theta that we're looking for. So, right, law of sines means we're looking for a side angle pair. Well, here's my angle theta and the side opposite it. So there's one side angle pair. And then for my other side angle pair, I've got my side at 27 meters, and it corresponds to the 90-degree angle right there. And so we can set up a similar ratio. Remember to always put the side on the top of the fraction, and then the angle goes inside the sine function. So with my orange side angle pair, I've got 17 all divided by sine of theta. And for my purple, I have, let's see, 27 all divided by sine of 90. And so, just like before, we will cross multiply to solve. When I do that, I get 27 sine of theta is equal to 17 sine of 90 degrees. And then I'm going to get rid of that 27 being multiplied. So I'll divide both sides by 27, which leaves me with sine of theta is equal to, and then I'm going to take that whole right side and plug it into the calculator. 17 times sine of 90, all divided by 27, is 0.629629,626. And in this case, I'm writing out all the decimals that my calculator is giving me because I'm not at my final answer yet, so I don't want to round and introduce more inaccuracies. And hey, this should look familiar. We've got sine of theta, and we're trying to solve for the angle, so we're going to have to use the inverse sine function. So we will apply the inverse of sine to both sides, and also to the other side. And on the left side, inverse sine and sine are opposites of each other, so they will cancel out. Inverse operations cancel out. And then on the right side, we'll just plug that into the calculator. And I get 39.0 degrees. Now you may be thinking, but hey, Miss Lamb, I didn't actually need to use the law of sines in order to solve for this angle, because if I know this one is 90 degrees and I know this one is 51 degrees, then I know, just like last time, the three angles in the triangle have to add up to 180 degrees. And you would, of course, absolutely be right. And you will note that it does, which is a great way of checking your work. But I did want to show you an example with the law of sines anyways. Okay. There is one other triangle tool that applies to all triangles, and it is called the law of cosines. So, the law of cosines. The law of cosines formula looks like this. It is c squared, so lowercase c squared is equal to lowercase a squared plus b squared minus 2ab, all lowercase, times the cosine of capital C. So that is what the law of cosines look like. Again, be intentional with your lower cases and upper cases. This is our only capital, so this is our angle. All these other three things are side lengths. Things to note about this formula is that angle C and side little c need to be paired to use this formula correctly. And by paired, I mean an angle with its opposite side, just like with the law of sines. And so to use this formula, oops, what did I write before? To use this formula, we have two situations that we can apply. So situations. There are two situations where you might want to use this formula. Situation number one is given three sides of a random triangle, find one angle. And situation two is if you find two sides, or given two sides, and the angle between them find the opposite side. Right, so there are two situations where you might want to use the law of cosines. The first one is if you have all three sides and you want to find an angle. The second one is given two sides and the angle between, find the opposite side. So the law of cosines applies to all triangles. Now let's look at each of these situations. So situation one. So in number one, let's draw an obtuse triangle. Situation 1 is given 3 sides. So we'll call this side 10 meters. We've got 17 meters and we have 11 meters. And let's say we're trying to find this angle down here. I'll call it theta. So with law of sines, the one we just did, it did not matter so much which one you labeled your A, B, and C. With law of cosines, it does. And so it's all based on this important fact: angle C and sine C need to be paired to use this correctly. So I've got 3 different sides and only one angle. Look for the one side angle pair that you've got. So in this case, that is the side 10 meters and our angle theta. So there's our side angle pair. And so the side 10 is going to be little c, and theta is going to be my capital C. With A and B, the labels don't matter. So labels for A and B don't matter. The reason it doesn't matter is because if you look at the formula, you end up adding these two numbers and the order of addition doesn't matter. And then here you're multiplying the two numbers and the order of multiplication doesn't matter either. So I wouldn't sweat that too much, but do figure out where your side angle pair is, because that is going to dictate which side is side C and angle C. All right, so C squared in this case is 10 squared is equal to A squared plus B squared, so the other two sides, say 11 squared plus 17 squared, minus 2AB, so 2 times 11 times 17, times the cosine of our angle, so times cosine of our unknown angle, theta. So if I want to find theta, I need to solve that equation. Let's get to it. 10 squared is 100. One thing to be careful of is students have a tendency to take this whole chunk and plug it into the calculator. You can't do that because you would be breaking order of operations. The reason is you would be using this subtraction before the multiplication. So you can't just take all the numbers and plug that into the calculator because you have to respect the multiplication here with our unknown. The thing you can do is you can compute that 11 squared plus 17 squared. Oops. So 11 squared plus 17 squared is 410. And we can also compute the negative 2 times 11 times 17. So this is 374 cosine theta. And again, fight the temptation to subtract these because you can't. We have to respect the multiplication. We have to do multiplication before subtraction, and so we cannot just jump right ahead to subtracting those two. The way we solve for theta at this next step is by going through our inverse operation. So that's subtracting 410 from both sides. So that's negative 310 is equal to negative 374 cosine theta. Another common mistake here, don't forget to bring that negative sign down. And then, to get cosine theta by itself, we will divide both sides by negative 374. So we've got cosine of theta is equal to 310 divided by 374. I'm going to write out all my decimals because I don't want to round yet. I haven't gotten to my final answer, 7700053. And now I will apply the inverse cosine function. So apply the inverse cosine to the left, inverse cosine to the right, and the inverse cosine of 0.828, etc., is 34.0 degrees. And then let's see an example with number 2, situation number 2. It says we're given two sides and the angle between them. Given two sides and the angle between them. Let's see. It's almost a triangle. With these labels. Centimeters, we have an angle 41 degrees and x. So situation 2 is given two sides and the angle between them. What I mean by that is I've got my side 29, my side 13, and the angle between them is 41 degrees. So that's my given information. If that's the case, I am able to find the opposite side, which is our missing value x. And so just like before, start by looking at your side angle pair. Be very clear that is your lowercase c side and your capital case C angle, and then work from there. So here is little c. And again, our labels for a and b don't matter. So in this case, we've got x squared is equal to 29 squared plus 13 squared minus 2 times 29 times 13 times the cosine of our angle, 41 degrees. The lovely thing about situation 2 is that if you look at the right side of this equation, you'll notice that it is nothing but numbers. And so we can actually just take the whole right side and plug it into the calculator. I do actually recommend that we do it all at once. So type in the whole right side all at once, because that way you're less likely to make order of operation mistakes on your own. And so what you get is 440.9489765. I'm writing out all of my decimals because I don't want to round before I'm getting to my final answer. And then, well, we've got x squared on the one side, so what we have to do to get x by itself is take the square root. Something we haven't done in a while. We'll take the square root of both sides. And on the left, the square root and the square will cancel out. And what I'm left with is 21.0 centimeters. All right, there is one final topic in these notes. I apologize because I know that it's long. And that last topic is the area of triangles. So we've gone through all these tools, sine, cosine, and tangent as ratios, the law of sines and the law of cosines, and all of these tools are all about finding missing sides and angles of triangles, sometimes right triangles, sometimes any triangle. The last fact about triangles that we will cover is about area. The area of triangles. And there is a formula that I believe most everyone is comfortable with, but there's also a second formula that we're going to introduce today. So formulas, if you are given a base and a height, then the one we've learned before is a equals 1/2 base times the height. There's also another formula, which is a equals, so area equals 1/2 AB, AB sine capital C. And in this case, so AB sine C is basically two sides and the angle between them. So just like the law of sines, or sorry, the law of cosines. All right, let's just see one example of this formula, this new area formula. in action. So draw out a triangle. We'll call this 8 centimeters, 6 centimeters, and 85 degrees. All right, so if you wanted to find the area of this triangle that I just drew, you can't use the 1/2 base times height formula because we don't have the height. But we do have two sides and the angle between them. And so we can use this new formula 1/2 AB times sine C. Remember, the capital C is our angle. So the way we plug this in is 1/2 A and B. Again, that label doesn't matter, so just multiply the two sides, 8 times 6 times sine of 85 degrees. So if we take the whole right side of that and plug it into the calculator, what we get is 23.9 centimeters squared. Anytime we're finding area, because it is a two-dimensional shape, right? It's not just one length, it is a two-dimensional space, our units are always squared. So if the sides were centimeters, then the area is centimeters squared.